Welcome to the Explainer. Ever wonder what actually happens in those milliseconds right after you click Buy Now? Today, we're going to pull back the curtain on the hidden engine that powers, well, pretty much everything you do online, database architecture. So here's our game plan. We'll start with that simple click, then map out the system's blueprint. After that, we'll dive into how data is organized, see how it all mirrors the real world, and then we'll finish up with the secret sauce that makes the whole thing work so well.
Okay, let's jump right in. First up, what is going on behind that click? It seems so simple, doesn't it? Just one click. But that single action kicks off this incredibly complex, perfectly coordinated sequence of events deep inside the application's architecture. So to handle that click, pretty much all modern applications use this really clever blueprint. It's called the three-tier architecture. Let's break down what that actually means.
The real genius of this structure, and you'll see this as a theme, is how it separates the major jobs into independent layers. And that separation, that is the absolute key to making the system both powerful and flexible.
The best way to get your head around this is with an analogy. So think of a restaurant. The presentation tier is the dining room, right? That's where you, the customer, place your order. The application tier, that's the kitchen, where the chefs actually process that order. And the data tier, well, that's the pantry, where all the ingredients are stored and managed.
You can see how this model creates this beautiful separation of concerns. What you see, the user interface, is completely separate from the business logic running on the server, and that logic is separate from the data storage itself. This is so critical because it means developers can go in and update or fix one layer without breaking the others.
Okay, so we've seen the application's three big tiers. Now let's zoom in on that final one, the data tier. Because, believe it or not, the database itself has its own internal three-level architecture. It's like layers within layers.
This is what we call the three-schema architecture, and its entire purpose is to create a separation between how we view the data as users and how it's physically stored on a disk.
So at the very top, you have the external level. That's your specific view, what you see on your screen. In the middle is the conceptual level, which is the big, unified blueprint for the entire database. And then way down at the bottom, you've got the internal level, which handles all the physical nuts and bolts. You know, how the data is actually arranged in bits and bytes on a storage device.
Now, to really get this, we need to understand the word schema. It sounds a bit technical, but really just think of it as the database's blueprint. It defines the structure, kind of like the column headers in a spreadsheet, but it doesn't hold the actual data, just the rules for it.
And here's where we see the key difference. The schema is that fixed structure, right? The empty spreadsheet columns. The instance, on the other hand, that's the actual data you fill into those columns at a specific moment in time. So the schema is the plan. The instance is the reality. So how do we decide on the right schema to start with? I mean, where does it come from? That's the job of something called a data model. It's a framework we use to translate messy, real-world information into a clean structure that a database can actually understand and work with.
Put simply, a data model is just a way of describing real-world things, like students or products or bank accounts, and the relationships between them in a logical way that makes sense to both people and computers.
For a long time, the most popular approach has been the relational model. Its power is in its simplicity. It just organizes everything into tables with rows and columns. It's not only super intuitive, but it's also the foundation for powerful languages like SQL, which lets us ask really complex questions of our data.
And here is a perfect example. We take a real-world entity, a student, and represent it as a table. Each individual student becomes a unique row. We often call that a record. And their specific details like ID, name, and mark, they become the columns or attributes. It's just a beautifully simple and organized way to manage complex information.
Okay, let's tie all of this together. This whole layer design, both at the application level and inside the database, it all gives us one ultimate benefit. It's a really powerful concept called data independence.
This is the real magic of this whole setup. It means you can make huge changes behind the scenes. Say you upgrade your hardware or you optimize the file structure without breaking the application for the user. The flexibility this provides is just incredible. And this independence comes in two main flavors. You have physical independence, which means you can change how the data is physically stored. Maybe you move it to a faster disk, and the application doesn't have to change at all. Then you have logical independence, which lets you change the conceptual structure, like adding a new email column to a customer table, without having to rewrite all the parts of the app that don't care about that new column yet.
So why does all this layering really matter? Well, the key takeaway is that this isn't just some abstract design. It's what allows our applications to scale. You can upgrade the database server without touching the user interface. It makes them way more secure by isolating the data behind all these layers of logic, and crucially, it makes them so much easier to update and maintain. It's really the fundamental blueprint for building strong, adaptable digital systems. This layered structure is the invisible foundation supporting our entire digital world, everything from your social media feed to your bank account. It has served us incredibly well for decades, but as we dive into an age of AI, massive data sets, and apps that are way more complex than ever before, it leaves us with a pretty critical question to think about. How might this architecture have to evolve to power the applications of tomorrow?